Question number 23 from the rotational motion additional exercise of NCERT. A man stands on a rotating platform with his arms stretched horizontally, holding a 5 kg weight in each hand. The angular speed of the platform is 30 revolutions per minute. The man then brings his arm close to his body with the distance of each weight from the axis changing from 90 to 20 centimeter. Okay. The moment of inertia of the man together with the platform may be taken to be constant and equal to 7.6 kilogram meter square. What is the new angular speed? Is the kinetic energy conserved? If not, from where does the change come about? So there is a man who is holding 5 kilogram weights in both his hands and who is standing on a rotating platform. Okay, so we have a platform here that is rotating. The man is standing on the platform. So this platform is rotating like this maybe. The man is standing on it. The moment of inertia of the man along with the platform is given to be 7.6. The man holds 5 kilogram weight in both his hands. So these are 5 kg weights. The 5 kg weights. Okay, then while the rotation is still going on, the man folds his hands. So maybe he folds his hands like this. So on folding his hands, the weights will get closer to the man. So he folds his hands like this. So he folds his hand and brings these weights closer to him. So the distance of these weights change. So he does this. So the weights previously were 90 centimeter away, and now each of them is 20 centimeters away from the axis of rotation, that is from the man himself. Okay, so whatever work the man is doing is his internal energy. The work is being done using the internal energy of man. So there is no external torque. So since the external torque, the net external torque on this system is 0, the angular momentum of this system is conserved. This comes from law of conservation of angular momentum, or loco-arm. Okay, so we'll use this law of conservation of angular momentum to find the answer to the new angular speed. Okay, so initial angular momentum and final angular momentum are same. Therefore, initially there are two things actually, the man himself and the masses. So initial moment of inertia, initial angular velocity is final moment of inertia, final angular velocity. Therefore, initial moment of inertia is the moment of inertia of the man plus the rotating table plus the table plus the moment of inertia of the masses that the man is holding. So we call them Im, and initial angular velocity omega I is given to be 30 revolutions per minute. So this is 30 revolutions per minute. So for right now we are not changing the units. For later, if some kinetic energy or something has to be found out, we'll convert the revolution into radians per second, revolution per minute to radians per second. Final moment of inertia. So the table and the man's moment of inertia remains the same, but the masses are brought closer. So this changes, and this is final angular velocity. Okay, so you have to find out the final angular velocity. So the final angular velocity is 30 times the moment of inertia of the man in the table. This is given to be 77.6 plus there are two masses, two 5 kilogram masses. So this gets multiplied with 2. So 2 mr square. 2 mr radius is 90 centimeters. So 0.9 square. This is divided by this bracket. So this bracket is 7.6 man plus table plus mr square. So 5 kilogram is the mass of the weights the man is holding, and this new distance changes to 20 centimeters, so 0.2 squared. Okay, so we calculate this. This is 30 times 76 plus 0.9 square is 0.81 into 10, so 8.1 plus 7.6. This gives us 15.7. In the denominator we have 7.6 plus 0.04 and 10, so that is 0.4 plus 7.6 gives us 8. So we calculate this. So we multiply 30 to 15.7, divide that by 8, we get 58.875 revolutions per minute. So this is the new angular velocity. So we can see the angular velocity has increased from 30 to 58.875 revolution per minute. This can be converted to radians per seconds also. So for radians per second, which is the standard unit, so it's a good habit to convert that. So this is 2 pi, one revolution is 2 pi radian and 1 minute is 60 seconds. So we get 6.165. So the final angular velocity is 6.165 radian per second, or 58.875 revolutions per minute. Okay, so this solves half the question. Let's call this part A of the question. So this solves part A. Is the kinetic energy conserved in this process? So for that we have to check the initial and final kinetic energy. Now the initial kinetic energy is half initial I omega I square. So half initial I is this thing. This is initial I. So that is 15.7. Initial omega. So omega I is 30 revolutions per second. But for kinetic energy we have to convert it to radians per second. So for revolution per minute, we again multiply 2 pi by 60, square this number. So this number is basically pi square. So this comes out to be 15.7 by 2, that is 7.85 times pi square. So this gives us 77.48 joule. So this is the initial kinetic energy. For final kinetic energy, we'll have to repeat this procedure but with the final values. So the final omega is this thing, 6.165, and the final moment of inertia, the net moment of inertia is this. So the denominator, 7.6 plus this thing, so that is 8. This is the final moment of inertia. So for final kinetic energy, we have to do half final moment of inertia, final omega square. So that is half 8, and the final omega F is 6.165 squared. So this gives us 4 times the square of 6.165. So that's around 38. So this gives us 152 joules. So the final kinetic energy is 152 joules. The initial kinetic energy is 77.4 joules. So the kinetic energy is more than doubled. So not more than doubled, it's almost doubled. So the final kinetic energy is greater than the initial kinetic energy. And the question is, where does this kinetic energy come from? No external work is done. So whenever there is no external force or no external torque, the momentum has to be conserved. The linear momentum and the angular momentum, they have to be conserved. The angular momentum has to be conserved when external torque is 0. That does not necessarily mean the kinetic energy of the system is conserved too. The total energy is conserved. The total energy, remember guys, the total energy of a system is always conserved. Total energy is always conserved. But the forms of energies are being converted into each other. So here the internal energy, which internal energy? The muscular internal energy. The boy has to flex his muscles. He has to use his muscles to fold his hands to bring the weights closer to his body. So the internal muscular energy is being used to increase the kinetic energy of the system. So this extra 152 minus 77.48, so around 74 joules of extra energy comes from the muscular or the internal energy of the body. Okay, I hope this clears this.